let's examine a couple theorems that don't really get used a whole lot, but it's nice to get a little more comfortable with what's going on with vectors and their cross products. So if you have two three-dimensional vectors, u and v, they are parallel if and only if their cross product results in the zero vector. Now, the thing is, the the zero does have an arrow above it, and that's because the cross product always results in a vector. So that notice that that arrow here needs to be here. That's different from a similar thing we saw for dot products where it was a zero scalar. So for example, because the vector 2, 4, -5 happens to be parallel to 4, 8, -10, if you take the cross product, you're going to get the zero vector, which we didn't work through, but just you can work through all those details if you'd like. As an experiment, I'd like you to pick any 3D vector you want. So pick an arbitrary 3D vector called u. In other words, you've needed to pick three numbers, which I don't know what they are, but let me call them u sub 1, u sub 2, and u sub 3. Those are your three. Those are the three scalars that you had picked, and those will become the components of a vector called u. Now I can tell you what the cross product of your vector and the zero vector is. I mean, if I start setting it up, so 3 by 3 determinant, your numbers that you've picked go here. I don't know what they are, but there's these zeros here. And what that's going to eventually do, I've skipped the work, is it's going to lead to 0i plus 0j plus 0k. And what happens then is no matter what 3D vector u is, then the vector u cross product vector, the zero vector, will always end up being the zero vector. Here's an idea that we will briefly come back to in the last chapter. So if you don't remember this, not a big deal now, but I think it's just helpful to mention right now that the two vectors u and v in 3D space would can be two sides of a parallelogram. And let's say you'd like the area of that parallelogram. Well, that can be found using a cross product. What you do is you take the cross product of the two vectors, so you get a new vector, and that vector you just look at the magnitude of. So somehow it's odd, but the magnitude of another vector ends up being the area of this parallelogram. So let's do that, right? So let's find the area of the parallelogram determined by these two vectors. Well, what we should do is take the cross product of these two, and we'll end up with 9, 13, -5, and that's a vector. But that's not going to be the area. We should take that vector and now apply the magnitude formula to it, right, in order to get the area. So the area of the parallelogram, like up here, what's shaded in brown, is going to be the magnitude of this result of the cross product. And in this example, that's going to be root 275.